You asked me something it like about limits and continuity, and it goes like this. If a function is continuous, the limit always exists. The problem is if it's not continuous, it sometimes exists. And we can talk about each of those examples. So, for example, let's say you want to find the limit as x approaches 1 of x squared plus 3x plus 5. This is continuous, so you just take this number and you put it in for x. So that's 1 plus 3 plus 5, which is 9. But let's say you wanted the limit as x approaches 2, absolute value of x over x. Okay, so this works for some points. Like for this one, it would work because it becomes absolute value of 2 over 2, okay, which is 2. But what about at 0? Well, we have a problem because the absolute value of 0, well, the absolute value of 0 is 0, and you can't divide by 0. So if it's continuous, you're in good shape. But if it's not continuous, then sometimes it exists, and lots of things can happen. And that's kind of where you get a lot of work happens in first part of calculus, is look at these limits. So one you actually might see on a test would be like limit as x approaches 1 from the right of 1 over x minus 1. So maybe in your head you can see a picture of this graph. It has a vertical asymptote at 1, and it looks like this, and then the other side of the graph looks like this. So this plus right here, this literally means from the right. So you traverse the curve from the right approaching that value. You're approaching 1, you're traversing the curve this way. And what you're looking for is what is the y value? What is you're always looking for the y value in terms of a limit. So what is the y value as this goes up and up and up and up forever?
Positive infinity.
Positive infinity. This becomes positive infinity. So the limit as x approaches 1 from the left, that means from the left. When it's to the right, it means from the left, 1 over x minus 1. So from the left, going this way, from the left, just to make it really clear, it goes to minus infinity. So we can summarize here and we can say that one-sided limits always exist. Okay, but what is the limit in this problem? What is the limit as x approaches 1? Well, the problem is it doesn't approach the same value. It does not exist. And from one direction it approaches negative infinity, from another direction it approaches positive infinity. They're not the same.
If it was like a removable discontinuity, then
yes,
it would approach the same thing, right?
Exactly. So that's kind of the simplest way we can go through a little bit of this without getting too mathy or complicated. But to answer your question originally, if it's continuous, the limit always exists. If it's not continuous, sometimes it exists, depending on the situation and the value, things like that.
Okay.
Okay.
That makes sense.
Where should we go? What can we what do you have next on your list there to talk about?
From the packet from yesterday.
Okay.
Can we do a few on page 557 between 23 and 40?
All right, I'm getting caught up to here. I got to re-download this. I got to re-download this this thing. So you said page
557.
557.
And it's section 10.2 within the
10.2. Okay, I found it. Okay, I'm there. Which numbers?
Any of them between 23 and 40.
23 to 40. Okay. A big list there. Okay, so
Yeah.
let's do, it's not really a starter problem here. Okay. Let me make a starter problem, and then we'll do a real one here. So n equals 1 to infinity, 1/2 to the power of n. Okay,
Mhm.
this is our starter problem. If you were to write out a few terms of this, you would say, okay, it's 1/2 plus 1/4 plus 1/8 plus 1/16, and you would hopefully see that this is geometric with r equal to 1/2.
Yes.
So if you can get something to the power of n, that's always your r. And the sum of this thing is equal to a1, which is the first term, 1 minus r, only if the absolute value of r is less than 1. So we've satisfied that here.
Yes.
So we're good there. What is a1? Well, a1 is the first term. It's whatever this tells you though. Like if this was 2, we'd be looking at 1/4, but it's 1, so it's 1/2. And it is okay. It is definitely okay that these are the same. Like it can happen. So your sum is 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which is 1.
Hmm.
So the game here, the game in these problems is we're going to see if we can put them into this form and then come up with the sum here. So I'm going to grab 24 first. So for 24, you have to first write the formula for the sequence. Like you want to write this as sigma something here to the right, and then n equals something to infinity.
Hmm.
So what I'm seeing here, I'm seeing there's always a 4 on the top. There's always a 5 on the bottom. Okay, but and let's say we want to start at n equals 1, just because we like that. How do we get 3 as an exponent? What needs to go here to get a 3 when n equals 1?
3
A 3, yeah, but in terms of n plus what value?
plus 3, 2.
2.
Oh, n plus 2 because n is
N is
okay.
1. So n is 1. So what you're trying to figure out is does this give you this? And it does. And so that's kind of the hard part here to start out, is you have to write this plus this. So 4/5 to the n plus 2. The problem is it's not in this sort of starter form where it's to the power of n. We want it to be to the power of n. It's to the power of n plus 2. So there's rules. If you have x to the n times x to the m, this equals x to the n plus m.
Mhm.
So we want to go backwards. So this is sigma n equals 1 to infinity 4/5 to the n times 4/5 to the power of 2.
Right.
Because this we know to take the sum of. This we're not really sure what to do with quite yet. So we'll simplify n equals 1 to infinity 4/5 to the n. This is 16 over 25. You can bring constants out of the sum. So this
Oh,
becomes
right.
16 over 25 sigma n equals 1 to infinity 4/5 n. So this part right here is what we're going to use the infinite sum formula. So the sum is a1 over 1 minus r if the absolute value of r is less than 1. What is r in this case?
The common ratio 4 over 5.
Yeah, 4/5. It's always this number in parentheses if you get it to the power of n, just n. Not negative n, not n plus 1, just n. That's your r. What is your first term? Well, you get that by putting 1 into this. So your first term is 4/5 to the power of 1, which is 4/5. Again, sometimes these are the same. It's not always, but sometimes they are.
Okay.
Okay, so now to find the sum of this, the sum is, this part is a1 4/5 over 1 minus 4/5. So that's all of this. And then you have the 16 over 25 off to the side here.
Right.
This is 4/5 over 1/5. And then the 5s cancel. So you have 16 over 25 times 4. over 1. That is 64 over 25.
Okay.
All right, so let's look at some of these other ones that we'll look at 28 next. So these do not always converge. Okay, they converge if they sum. They sum if r is less than 1. Absolute value of r is less than 1. So here, this is r. Is r less than 1 in this one? Is pi over e less than 1? No.
No.
So this one diverges. And that means there is no sum.
Okay.
You don't have to say that, you just say diverges, but that is the case there. So sometimes they make them look like they don't converge. We'll look at 29 next, but they actually do. So this is not in the form that we talked about. It's not to the power of n. It's e to the minus n. And there's some property here. So if you have x to the n to the m, this equals x to the n times m. We're going to go backwards here. We're going to rewrite this as e to something to something. And we really want n out here. So that means this has to be a -1 there. So this now becomes 1 over e.
Oh, which is
Less than 1. Yeah, r is equal to 1 over e, which is less than 1. So you're good. Okay, so this one's a little bit harder because the sum it's still a sub 1 over 1 minus r. We have r, but what's the first term? The first term is, you have to put 1 into this. So that's e to the -1, which is 1 over e.
Right.
Okay, and I would assume your instructor expects you to be able to reduce something like this. So to do that, on the bottom, you have to make a common denominator. So it's e over e minus 1 over e. This is 1 over e minus 1 over e. The e's cancel, and you get 1 over e minus 1.
Okay, nice.
Okay. I'd like to do one more, either 26 or 31. Well, or two more. I mean, there's a few more here we could do. So that's where you got to tell me how many more you want me to work through. 26 is good. 31 is good. 36 is good. I mean, really, any of them are good, but
Let's just do 31 then.
okay. Okay, so similar to limits, that you just have to try to rewrite some of these things to make it into the form you want. So this is really 8 over 5 to the n plus 2 to the n over 5 to the n. And there's a sigma here. So you can actually break these apart into two different sigmas. So it's sigma 8 over 5 to the n plus sigma 2 to the n over 5 to the n. And then on the right, I think this one's easier to see. This is 2/5 to the power of n.
Yes.
This is really 8 times 1 over 5 to the n on the left. And it can be written even further as 8 times 1/5 to the n, because 1 to the n is always 1. So that's why you can always do that.
Okay.
So this is all about being able to manipulate the original. This 8 comes out. This is 8 sigma 1/5 n plus sigma 2/5 n. Okay, so in each of these cases, you're starting at n equals 0 to infinity, n equals 0 to infinity. So for this first one, let's actually do the one on the right because it doesn't have a coefficient. The one on the right, your r is 2/5. What is your a1? You're putting 0 into this. Anything to the 0 power is 1. So your a1 is 1. So the sum on the right here, the sum of all this, is 1 over 1 minus 2/5.
Okay.
So we'll come back to that. On the left here, your r is 1/5, and your a1 is 1 for the same reason. Anything to 0 power is 1. So it's 1 over 1 minus 1/5, but you got this times 8 over here to bring down. Now it's just your ability to deal with these fractions. So it's 1 over 4/5 times 8 plus 1 over 3/5. So on the right, it's 5/3. You flip the fraction. On the left here, it's 5/4 times 8, which is, you always divide before you multiply. So it's 10. 10 plus 5/3. So 10 is 30/3. And you get 35/3 as your final answer on that. Key though really is back up here. It's seeing how to break apart this thing into these other pieces.
Right. Okay. That makes sense.
Yeah. All right. Where should we go from here?
Can we do number 2 on page 296?
Yes, 296, number 2.
That's in the chapter 5 on the PDF.
There it is. Number 2. Okay.
The one about the ostrich.
Yes. Wonderful ostrich. Okay. Can I get this in? Slip this in. All right, an ostrich runs with velocity 2 kilometers per hour for 2 minutes, 12 kilometers per hour for 3 minutes, and 40 kilometers per hour for another minute. Compute the total distance traveled and indicate with a graph how the quantity can be interpreted as an area. Okay, so one of the problems here is you got units that are not correct. 2 minutes is 1 out of 30 hours. 3 minutes is 1 out of 20 hours. And 1 minute is 1 out of 60 hours. Okay, so we know that distance is rate times time.
Yes.
So this is a rate, this is a time, you multiply them together. So you're making rectangles. You have essentially have a graph here. Let me make a clean graph down below here. So this is velocity. And the first one is 20 kilometers per hour. So I'm gonna call this 20, okay? And this is where it gets a little bit, these won't make any sense, but this is gonna be 1 out of 30. Okay, and then for, well, we can do it. So that's really 2 minutes. Let me do it different. Let me not do it that way. That's very unclear. So this is 2 minutes, but we know that it's really 1 over 30 hours. Okay, and then we go for another 3 minutes, and the thing instantaneously drops to 12 miles per hour. So we'll call that 12, and that's 5 minutes, but we called that 1 over 20. And then instantaneously gets back up to 40 and does that for another minute. So that's 6 minutes right there, which we know is 1 over 60. Okay.
Right.
So these are the rectangles that you're finding the area of. Okay. And the interpretation is just how far did it go. So the distance is equal to 20 times 1 over 30 plus 12 times 1 over 20. Just to be clear here, this width is 3 minutes, and that's how I got the 1 over 20. And 1 minute is 1 over 60. So 2 minutes times there are 60 minutes in 1 hour. That's how I'm getting the 1 over 30. Then the 3 more minutes, yeah, just to be clear here. Okay, plus 40 times 1 over 60. And that gives you the, whatever that number is, you need to calculate. Well, I guess, it's 2/3 plus 12 over 20, which is 3/5 plus 2/3, and that's in kilometers. All that, so you add that together. Let's see, 4/3 plus 3/5. So we'll make a denominator of 15. 20 plus 9, so it's 29 over 15 kilometers traveled.
Okay. And it's like area because when you graph it. Okay. I
Yes,
see.
it's velocity and time.
Okay, that makes sense.
Where should we go from here?
Can we do number 60 on page 118? It's the second page. Second page, yeah, second page.
Okay, sure. Number 60. Okay. All right. So you're trying to find the limit. Are you trying to find the limit or the horizontal asymptote? Oh, the limit at infinity. Okay. So you're supposed to find, there's two things you're supposed to find. Like part A is the limit as u goes to positive infinity, and part B is the limit as u goes to negative infinity. Is that okay?
Mm-hmm.
That's that understanding is okay. Um,
Yes.
I know you won't be able to do this on the exam, but I'm going to graph it and snip in a picture of this if you haven't done it already, because we are trying to learn something here. So let me
Mm-hmm.
get that up. And then we'll do it by hand so you can see how to do it by hand. But we got 8x minus 3 over square root 16x squared plus 6. Okay. So a couple things when you see the graph here, you're going to notice that there are two horizontal asymptotes. Okay, there's one at y equals 2 and one at y equals minus 2. Hopefully you see that there and there. Maybe you haven't seen that before.
Yes.
Okay, so then the question is, well, how do you do this by hand? Okay, so first thing you do when you look at this function is you say, what's the biggest power in the numerator or the denominator? You might say u squared. Okay, but there's always a but. It's the square root of u squared. And this is a long forgotten thing. The square root of u squared is actually absolute value of u, which
So it
means
can be plus or
it's,
minus.
yeah, it's u when it's positive and it's minus u when it's negative. So let's do the easier one here. When we're trying to find the limit out at positive infinity, what you do is you divide both the top and bottom by positive u. Let me try to grab this and make this clear. So when we're trying to find the limit as u goes to positive infinity, we write 8u minus 3 over u divided by the square root of 16u squared plus 6 over u. Did you see any of this in
Okay.
class?
This
Madison.
appears new.
Okay. All right. Well, so this is, you'll see this again in calculus, but well, no, you won't, because you said you're not taking it. So you have to figure out the highest power and then you divide. Now on the bottom is really where the issue is, because what you're really going to do here is you're going to end up writing 16u squared plus 6 over u squared. Okay. And the reason you can do that is
Okay.
the square root of u squared is u. It's like, so it works. Up
Right.
top here, it's 8u over u minus 3 over u. Okay. On the bottom, so the bottom, so this is 8. Sorry, let me do the top first. So the top is, we're going this way, is 8 minus 3 over u over. So this is the so it's the square root of 16u squared over u squared plus 6 over u squared. This comes over the square root of 16 plus 6 over u squared. It's the limit as u goes to infinity. And then so this is, so we've created this this is the thing we're doing after we do the simplification, dividing dividing and then moving u in. And then you have to remember here the limit as x goes to infinity, 1 over x to the n, where n is greater than 1, this always goes to 0. And you might say, well, okay, that maybe I get that, but how do I apply it here? Well, here's what it means. It means it's 8 minus, this is 0 right up here, because this is 1 over x or 1 over u. That's this right here. This 3 over u is like this. 6 over u squared is like this because n is 2, 2 is bigger than 1. So this goes to 0, 0. So it's square root of 16 plus 0. So this becomes 8 over the square root of 16, which is 8 over 4, which equals 2. And that's what we saw in the picture here. So
Okay.
are there steps here that are, now that you've seen it, like, can you do these steps? I know I go through them very quickly, but can you, really this is the big one where you divide by u, but then you change it to u squared inside the square root. Is that clear, kind of?
I understand the concept of the steps, and that is enough.
Okay, it's because there's the other side we have to do if you want, which is the negative infinity, and then you divide everything by negative u.
Okay, but this is how you find like horizontal asymptotes. Like you put the like. Okay.
Yes.
Okay.
So let me maybe this will be clear. I said just the negative u when you go to negative infinity. So the only thing that'll change in all this work that we did is is right here. This will become negative u. So that means this becomes negative 8. So that negative 8 propagates all the way down, and that's how you get, if we could show all this other work, you would get negative 8 over 4 equals negative 2.
Okay, that makes sense.
Okay.
This is more of like a conceptual question, and it's like infinite limits versus limits at infinity. What is that?
Okay.
Yeah.
So the limit as x approaches 1 over x minus 1. This is, well, let's say 1 from the right. This is positive infinity. We already did this. This is an infinite limit.
Right.
And then if I ask you what's the limit, so we use the same function. We'll say the limit as x approaches infinity, 1 over x minus 1. This is a limit at infinity. I think those are the words. I believe that's what you said. And this equals 0.
Yes.
This is the horizontal asymptote y equals 0. So the problem we just did, this one you just asked me about, this is a limit at infinity. Plus or minus.
Mm-hmm.
An infinite limit generally means vertical asymptotes. Like the graph goes up or goes down, something like that. But the key here, I think this will help you distinguish them for the short term, is if this is plus or minus infinity here, this symbol, then it's a limit at infinity.
Okay, I see. That makes sense. This is related, but on one of our midterms, she asked just straight up, there are 2 types of asymptotes. How do you find them?
So there's horizontal and vertical. So the horizontal is the limit as x approaches plus or minus infinity f of x. The vertical asymptotes only occur in a rational function. So a rational function is defined as p of x over q of x. And it's defined where q of x equals 0 if p of x divided by q of x does not divide, meaning no factors. So because if it divides, that means that there's a hole.
Right.
So another way you can write a rational function is a over bx minus c plus d, and this p of x q of x is this down here. It's just when you divide. this D is always the I'm sorry, this BX minus C is always this is the horizontal asymptote. This is the vertical asymptote. But if it was just that plain, like the way you said it, like what is, how do you find a horizontal and vertical asymptote? You need some context, because not even everything has a horizontal asymptote. Um, so it probably is in the context of rational functions.
Okay, that makes sense.
Because like, okay, let me just give you, because maybe you just taking my word for it. You could have a slant asymptote, and that doesn't have a,
Oh, right, yeah.
I mean, and it does have a vertical, but it doesn't have a horizontal. And the limit at infinity is infinity. And if I just said, like, if I just graph something like x squared, it has neither, because it just goes like that. So you need
Right.
like a constraint. You can't just study. You have to study for pre-calculus or study. You need to know what situation you're in, what box you're in.
Mhm. Okay, that makes sense. But to answer that, I could talk about, like, the
Limits
early.
at
Yeah.
infinity would be good.
Mhm.
Vertical are one-sided limits. If you're talking about it in terms of
Mm.
like limits, it's like the limit as x approaches 1 from the left, limit as x approaches 1 from the right. And I'll go back to the graph we had way up here. The vertical asymptotes here exist because the one-sided limits exist. See,
Right.
we went up, there's a vertical asymptote from the left. So, okay, maybe that is the discussion your instructor wanted. She wanted you to say that a vertical asymptote exists when one side goes to positive infinity and the other side goes to negative infinity, or they could both go to the same infinity.
Okay.
So just maybe this is too much, but like if it's 1 over x squared, this has this shape of graph for it. The limit as
Yeah,
x
I was
approaches.
thinking about that.
Okay, from the left here, it goes to positive infinity. From the
Mhm.
right, it goes to positive infinity. So the limit does exist because they go to the same thing. Um,
Okay. Right. Okay. Okay, that makes sense. Um, let's see. Okay. Okay. What is the difference between oh, wait. No, I know that. I know. Okay, I know what that is. Um, uh, can we do, just, like, the definition of an instantaneous rate of change versus a wait, what's the other one? It's AROC, the acronym.
average rate of change. Yeah. Okay, so let's say I think we'll make up something simple like x squared plus 6, and
Mhm.
let's first define average rate of change. This really means slope. So
Right.
I have to give you an A and a B. So let's say I say from 1 to 3. So your A rock, which I don't even like, but that is what it's called. It's f of b minus f of a over b minus a. This is like y2 minus y1, x2 minus x1, which is a slope. And this is like x1 and x2.
Mhm.
Hopefully you're seeing that. So this is in your example to be f of 3 minus f of 1 over 3 minus 1. So f of
Yes.
3, you can come back up here and get f of 3 is 3 squared plus 6. It's 15. F of 1 is 1 squared plus 6. So that's 7 over 3 minus 1. So it's 8 over 2, which equals 4.
Mhm.
Is that okay?
Yeah, that makes sense.
Okay. Now, to find the instantaneous rate of change, we have to know which value we're doing at. It's probably at 3. So we'll say at 3, instantaneous rate of change at x equals 3. We're essentially trying to find f prime of 3. So that's f prime of a. Or what we did last night, and that's probably what we'll do here, is we're going to find f prime of x. And that is the limit as h goes to 0, f of x plus h minus f of x all over h. So the f of x that
Yes.
I specified is x squared plus 6. And then x plus h is going to be x plus h squared plus 6. So you're foiling this, x squared plus 2xh plus h squared plus 6.
Mhm.
And then we're writing this formula on the right here. We're trying to find the limit as h goes to 0, f of x plus h. So all of this, x squared plus 2xh plus h squared plus 6 minus f of x minus x squared plus 6. This is your f of x all over h. So now it's just a matter of doing some algebra. You have to so the limit as h goes to 0, x squared plus 2xh plus h squared plus 6 minus x squared minus 6 all over h. And I mentioned before, your check is if you've done this correctly, all the terms that remain will have an h in them. 2xh plus h squared over h, they both have an h in them. You divide that out. So you have 2x plus h, and then that becomes 2x plus 0, which is 2x. Your derivative f prime of x is 2x.
Yes.
And then we
Okay,
have
and
to do
that's
it at
the
a point.
IROC.
Yeah, that's the IROC. So it's 2 times 3, which is 6. So the instantaneous rate of change is 6. The average rate of change is 4. Why are they different? So let's look at the graph of x squared plus 6, which I should regret not picking a different number. So let's assume these go by 2, 4, 6. So this is what the graph looks like. So at 3, the slope is very steep here. That's
Mhm.
the 6. But from 1 to 3, it's not as steep. This one has a slope of
Okay.
4, and that's why they're not the same, and they're not usually the same.
Okay. Yeah, that makes sense. And you said something about like instantaneous rate of change being a tangent line and average rate of change being a secant line.
Yes.
Okay.
So I can diagram it a little better. Let's say we're looking at something like the square root of x, which has this shape right here. If you pick 2 nice points, you connect them with a secant line like that. But at any point you might have a different shape of this tangent line. It just touches in one place. So think of a circle. You can touch it, that's a tangent line, or you can go through 2 points, and that's a secant line.
Yes.
And
Okay. That
and
makes sense.
the first one is this is an instantaneous rate of change. This is an average rate of change.
Mhm. Okay. That makes sense. And then this is kind of random, but I did this wrong on the last midterm, so I wanted to revisit it. Um, it's like it's one of the oh, actually, no. I have a question before that. Um, what's the difference between a sequence and a series?
Yes. Okay. So so we have you said sequence. and then series.
Mm-hmm.
So I'm gonna define a sequence an equals 1 over n. So the sequence is, and this is from n equals 1 to infinity. So the sequence is I've got 1 over 1 plus, I'm sorry, 1 over 1 comma 1 over 2 comma 1 over 3 comma 1 over 4 comma, and so on. The series is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. So the difference is the sequence is just the list, a list of the numbers. The series is the summing of them.
Oh, I see.
And
Okay.
they're often used interchangeably, but that's completely wrong and shouldn't be that way. As a student, you get a lot of grace because, I mean, you're just learning it, but a sequence is just the list of numbers. The series is when you add them together.
Okay, that makes sense.
So in some other ways, series always have a sigma associated with them, but they're not always written. Sometimes they're written in this is expanded form, and then this is like compressed form.
Okay. That makes sense.
And then the
And then
sequence just a sub n.
okay, I understand this now. Sequence list series sum. Sequence list.
Yes.
Okay, I
Yes.
understand that. And then this is just like a problem related to that, and it's determine if the following series converge or diverge. And
Yes.
it's like um goes to infinity, sigma n equals 0, and then the function is 8 times -1/2, and that -1/2 is to the second.
Like that.
Oh, I mean to the n, not the
To the power of
second.
n. Okay.
Yeah,
Yes.
sorry.
Yeah. So this is so we're gonna use some of the properties we talked about earlier. This 8 can come out.
Mhm.
This is sigma 8 sigma n equals 0 to infinity minus 1/2 to the power of n. This is geometric. Okay.
Yes.
And then r equals minus 1/2. Is the absolute value of r less than 1?
Yes, it is.
Yes. Okay. So this part definitely converges. This, well, okay. Let me say this another way. Sequences, they can either converge or diverge.
Yes.
Series can either sum or not sum.
Okay.
So here's the best path. The sequence converges and we know the sum.
Right.
But they can converge but not sum. And that's not great. If they diverge, they never sum.
Okay.
Okay, so the correct language is that the sequence converges or diverges. The series has a sum or does not have a sum.
Okay. That makes sense.
Now, getting back to this problem, the sum is a1 over 1 minus r. Your first term is for n equals 0 this time. So when you put 0 into this, a1 is 1, 1 minus 1/2. I know we're a little crammed in space here, but 1 over 1 minus 1/2 becomes 1 over 3 halves.
Which is just 2/3, so it converges to 2/3.
Yes.
Okay. That makes sense. Okay, I understand that now.
Okay, and then you have to multiply by 8.
Okay. Yes. Oh, multiply by 8.
Yeah,
Yeah.
yeah.
Okay.
So it's 8. So this becomes 2/3, but then you multiply by 8, and you get 16/3.
Oh, okay. Multiply by, don't forget the 8.
Yeah.
Okay.
So let me do another one here. So the um, um, okay, yeah. So let me make one up here. So 5/4 to the n, sigma 5/4 to the n equals 0 to infinity. 5 over 4 to the n This it's okay. We're using this wrong context. So let me not. This is not appropriate. Okay. So the thing that you want to focus on is most of the problems you're going to get are geometric, and you really are just looking to see if that r is less than 1. We saw a few examples earlier where it's not less than 1, and
Mhm.
then they don't converge, and so on. So
Okay. Yeah, that makes sense. I think I'm out of things.
okay.
Wow.
We got a couple minutes left if you want to look over your notes again.
Hmm. Mm. Oh, you've seen a lot of the material that's going to be covered on the test and like the list of things that I'm going to be tested on.
Yes.
So we get 2 pages for this one. And so far I have the like derivative definition thing with X and H to include on it. Sequence rules and sum rules and all the like equations for that. Um, the parameter equations, the polar equations, families of functions, just like a cheat sheet for me to
Yes.
see what means
Yes.
what, and the unit circle. Can you think of anything else that would be good for there?
I always like example problems if I'm not comfortable with something worked out. Um,
Okay. Oh yes, the limit continuity rule. Okay, that
yeah,
would
this
be.
would be good. These are the sometimes, always, never questions. Um,
Um.
I think um, the stuff with the r's less than 1. Those are good to have. Um, I think we covered some log properties last night.
Oh yes, that would be good. Yeah, I think that's pretty good, I guess. Yeah, I don't think I need anything else.
Okay. I will actually send the notes and screen recording out here within the next 30 minutes. Sorry for the delay on that. And
Oh, don't worry
thanks. Thanks for scheduling, and I'll see you next time, whenever that is.
about it. Okay, thank you so much.
You're welcome. Bye now.
Bye.